Okay, so in this video, I wanted to make a brief introduction into how you can perform nodal analysis into an AC circuit. So remember that nodal analysis basically consists of applying the Kirchhoff current law. Okay, what the Kirchhoff current law says is that if you have a node, remember that a node is a connection between different electrical elements. Well, if you have a node, this node uh, will be connecting different electrical elements, and we have different branches. Okay, here we have, for instance, a resistor, here another resistor, and here we have another element, no, maybe another resistor. But according to what Kirchhoff current law states is that if you have a current, let's say I, this current will be split between the different branches of the circuit depending of the resistance, no? So for example, here you have a current I1 and here we have a current I2. So the Kirchhoff current law says, okay, since the current will be split between the different branches of the circuit, we can say that the current that enters a node should be equal to the nodes that are leaving that node. Okay, so here in this figure, you can see that I is entering this node, but I1 and I2 are leaving. So the Kirchhoff current law states that, okay, all the current that is entering a node should be equal to the current that is leaving. Okay, so that is very useful because based on that, we can apply what we call the nodal analysis into an electric circuit. And in particular, we will use this basic principle in order to solve uh, an AC circuit, in particular this one that you can see right here. So remember that to solve an AC circuit, we need to convert all of the elements of the circuit into the frequency domain. So the first step is to take, for example, the voltage source that in this case has a sinusoidal behavior and convert that into the phasor representation. So here we have 20 times the cosine of 4 times t volts. And to convert to the phasor representation, we need to take the amplitude, that is the, and also the phase angle but here the phase angle is equal to 0 degrees. Okay, so basically we are converting this sinusoidal into phasor, that is basically taking the amplitude of the sinusoidal as the magnitude of a complex polar number, and the phase angle will be the angle of that polar number. Okay, so this is the way in which you can represent a polar complex number. Okay, so what else? Well, we also need to convert the resistance and the capacitor and the inductors into its impedance equivalent. So for example, here we have 10 ohms and the impedance of a resistor is equal to the same resistor. We also have a capacitor of 0.1 farads, and we can convert that into its impedance equivalent as 1 over J times omega times C, and this is equal to 1 over J times omega. What is omega? Well, the omega is determined by the frequency of the sinusoidal, that in this case is 4 radians over second. So here we have J times omega, that is 4, times C, that is the capacitance value, that is 0.1. And this will be equal to 2 minus 2.5 J ohms. Okay. We also can convert when obtain the impedance of the inductor. No, so the impedance of the inductor is equal to J times omega times L, that is the inductance value. So we'll multiply J times omega, that is 4 times 1. And this is equal to 4 J ohms. Okay. Also, we have here the value of the other inductor, that is 0.5, and we convert this into the frequency domain. So this is equal to J times omega times L. That is equal to J times 0 times 4 times 0.5. And this is equal to J times 2 ohms. Okay. And well, now that we have converted all the elements into the frequency or its impedance equivalent, we can rewrite the circuit. So here we have the voltage source that has a phasor equivalent to 20 with an angle of 0 degrees volts. Also, we have here the resistor of 10 ohms. Here we have the capacitor of 0.1 farads, which impedance is equivalent to 2.5 J ohms. Also, here we have the inductor of 1 Henry, that its impedance is equal to 4 times J ohms. And we have here a current source that is dependent on the current. One thing that I was missing here, and I need to write this in a different color, is that this current source, okay, is dependent on the current Ix. Well, the current Ix is the current that passes through the capacitor, okay? So that is important because this current source is dependent on the current that passes through this element. Okay, so we need to be careful about that condition. In fact, I will write this in the equivalent circuit right here. And well, what else? Well, we need to write the current dependent source that is equal to 2 times Ix. And here we have the inductor value of 0.5 Henrys that is equal to J times 2 ohms. Okay, so now the idea is that one of the important aspects is that we need to define the nodes of the circuit. So one of the important nodes in any circuit is the reference node. Typically, the reference node is the node in which the negative terminal of the voltage source is connected, and we denote the reference through this symbol. So here you can notice that we have here the negative terminal of the voltage source, and this is connected to all of these elements. Okay, and well, also the voltage in this node is equal to 0 volts. Okay. Also, we have another node here that I will label node 1, where we have a voltage V1. Also, here we have another node. Basically, remember that the nodes is the connection between different elements. So here we have another node that I will label node number 2 with a voltage V2. And here we have another node that I will label as node number 3 with a voltage V3. Okay, so here we have a voltage V3. Okay, so also it's important that we define the directions of the currents in the circuit. So for example, here we will have a current that are, in this case, I will label this current as I1, no? This current I1 is passing through well, it's going from the negative to the positive terminal of the voltage source, and then it goes to the 10 ohm resistor. But we have here a branch, no? Or different branches, because you have here a direction or a branch that where it is connected the capacitor, and also we have another branch where the inductor is connected. So this current will be split, no? In a current, well, here we have Ix, no? So I1 is split between Ix and another current that passes through the capacitor that I will label here as I2. Okay, so this current is going from the voltage source to the resistor of 10 ohms, and it is split between the capacitor and the inductor, okay? And the current that goes through the capacitor is Ix, or I sub x, and here we have I sub 2. Okay, that is the current that passes through the inductor. Another important thing is that, well, we need also determine what is happening in node number 3. So you can see that in node number 3, we have I2 that is entering this node, and also we have the current dependent source, the current source that is dependent on current that is also entering this node. So we should have another current that is leaving this branch, okay? And, well, that current is equal to um, I3, okay? That is basically the current that goes through this direction, okay? So we have defined the nodes, we have defined the currents, and essentially what we need to do is to apply the Kirchhoff current law to each of the nodes, okay? So for example, for node number 1, we can see that I1 is entering this node and I1 is the same current that is leaving, okay? Because it's entering this point and also is leaving this point through this direction, okay? And the interesting part is that we can compute that, remember that I1 is basically the current that is passing through the 10-ohm resistor. So we can compute the current I1 as the voltage of the 10-ohm resistors divided by the resistance, okay? But the voltage that it is applied in the 10-ohm resistor is equal to the difference in voltage between node number 1 and node number 2, okay? So the voltage of these resistors is basically the difference in voltage between these two nodes. So here we have V1 minus V2, okay? And we need to divide this by the resistance, no? That in this case is 10 ohms, okay? So this is the current I1, okay? And also, well, how can we compute? We can compute also the voltage V1. Why? Well, if you notice, the difference in voltage between V1 and the reference node should be equal to the voltage of the voltage source, okay? So we can say that V1 minus the reference voltage node, that is 0 volts, should be equal to 20 with an angle of 0 degrees volts. So we can say that V1 is equal to 20 with an angle of 0 degrees volts, okay? So I1 can be written as B1, that in this case is this value, that is 20 with an angle of 0 degrees volts, minus B2, and this is divided by 10 ohms. So this is the current that is moving along this branch, okay? And we can make a similar approach for the other nodes, no? This was for node number 1, and now we need to make it for node number 2. So if you analyze node number 2, you can see that I1 is the current that is entering, no, this node. But the current that is leaving is Ix plus I2, okay? Remember that according to the Kirchhoff current law, the current that is entering a node should be equal to the currents that are leaving that node. So here you can see that I1 is entering node number 2, and Ix is leaving node number 2, as well as I2 is leaving node number 2. Okay. Based on this, we can also compute the voltage Ix, because Ix should be equal to the voltage in the capacitor divided by the resistance, or in this case, the impedance. Remember that the impedance is essentially a resistance that depends on the frequency of the circuit. So we can compute the voltage of the capacitor, no? Because we can compute it as the difference in voltage between node number 2 and the reference node. So we can say that the voltage in this capacitor is V2 minus 0 volts. And this is divided by the impedance or the resistance, that is minus 2.5 J ohms. So Ix is equal to V2 divided by minus 2.5 J ohms. Okay? And also we can compute I2. Remember that I2 we can compute will be equal to the voltage of this element divided by the impedance or the resistance in this case. So here we have, well, we need to compute the difference in voltage between V2 minus V3 that in order to compute the voltage in this element. So we have here V2 minus V3, and this is all divided by the impedance, that is 4 times J ohms. Okay, so now we have well, we have defined all the currents in this node. So we know that I1 is equal to 20 with an angle of 0 degrees volts minus V2, and this is all divided by 10 ohms. And this should be equal to Ix, but we know that Ix is equal to minus V2 divided by 2.5 J ohms plus I2. But I2 is equal to this term, that is V2 minus V3 divided by 4 J ohms. Okay? So this is basically the way in which you can define the equations for node number 2. Okay? So this would be an equation, but we have two incognitas. We need to define another equation in order to have a system of two incognitas and two equations. And in that way, we can solve a system of equations. So we can define a similar equation for node number 3. So we apply again the Kirchhoff current law to node number 3. And you can notice here that we have here um, I well, we can see, no, if you look at node number 3, that I2 is entering this node, it, and also the current of the current source, well, the current source is entering this node, that remember that is equal to 2 times Ix, and I3 is leaving that node. So here we have I2 plus 2 times Ix should be equal to I3, okay, because I2 and is entering this node, and the current source is also entering this node, okay? And also we can see that I3 is the one that is leaving. That's why I'm defining the equation in this form, okay? And well, thanks to the previous note, we know the equations for I2 or the definition of I2, and also we know what is Ix. So to solve that, we can say that, well, we need to define I3 because we don't know the exact value of that. So I3, well, it should be equal to the voltage that is passing through this, well, that this element, no, or this inductor has, divided by the impedance, okay? And we can see that, or we can compute the voltage in this element as the difference in voltage between node number 3 minus 0 volts, okay? So that is V, sorry, so we have here V3 minus 0 volts divided by J2 ohms, okay? So now we can substitute all the values of the currents into this expression. So here we have V2 minus V3. No, this is the value of I2 divided by 4 times J ohms plus 2 times Ix. And Ix is minus V2 divided by 2.5 J ohms. And we also have here, well, this should be equal to I3, and we can see that I3 is equal to V3 divided by J2 ohms. Okay? So at the end, well, what you can see is that we have two equations and we have two incognitas. We have V2 and V3 in these two equations. I will mark them with blue, no? So these are the two equations. We have these incognitas, B2 and B3 are our incognitas. But with these incognitas and with two equations, we can solve for the two values. Okay. So you can ingress these values in your calculator in order to compute the value of B2 and B3. Okay. And if you do that, you will notice that the voltage of B2 should be equal to should be equal to 18.9736 with an angle of 18.4349 degrees volts. And B3 should be equal to 13.9140 with an angle of minus 161.56 105 degrees volts. Okay, but remember that the problem was asking us to compute the value of Ix. But we have already an expression for Ix that is equal to Ix should be equal to minus V2 divided by 2.5 J ohms. And this is equal, well, if we substitute the value of V2 in this expression, you will notice that the current Ix in phasor form is equal to 7.589 with an angle of 108.4349 degrees, and these are amperes. And we can express this in the time domain as 7.589 times the cosine. And we need to define the frequency of the circuit, that is 4. So we have here 4 times t with an angle of, or a phase angle of 108.4349 degrees. And these are amperes, okay? So this is the result of this exercise, okay? So as you can see, the trick here is that you need to first identify the nodes of your circuit and apply the Kirchhoff current law to each of the nodes. Okay, and you need to be careful about defining the relationships of the current and for the current, no? And you need to analyze very carefully your diagram, no? The trick here is in the diagram of the circuit. If you define correctly the diagram of your circuit, you will be successful in solving this type of circuits. But you need to make all this exercise with patience in order to have the correct result. Okay, so that will be all for this video. I hope you like it, and I will try to upload another video in which I solve another type of exercise. So see you later.